So it's taken us a lot of videos to get through the neural network learning algorithm. In this video, what I'd like to do is try to put all the pieces together to give an overall summary or a bigger picture view of how all the pieces fit together and of the overall process for how to implement a neural network learning algorithm. When training a neural network, the first thing you need to do is pick some network architecture. And by architecture, I just mean connectivity pattern between the neurons. So, we might choose between, say, a neural network with 3 input units and 5 hidden units and 4 output units versus one with 3, 5 hidden, 4 output, and here 3, 5 units in each of 3 hidden layers and 4 output units. And so these choices of how many hidden units in each layer and how many hidden layers, those are architecture choices. So how do you make these choices? Well, first, the number of input units, well, that's pretty well defined. And once you've decided on a fixed set of features x, the number of input units will just be the dimension of your features xi will be determined by that. And if you're doing multi-class classification, the number of output units will be determined by the number of classes in your classification problem. And just a reminder, if you have a multi-class classification where y takes on, say, values between 1 and 10, so that you have 10 possible classes, then remember to rewrite your outputs y as these sorts of vectors, right? So instead of class 1, you recode it as a vector like that, or for the second class, you recode it as a vector like that. So if one of your examples is takes on the 5th class, y equals 5, then what you're showing to your neural network is not actually a value of y equals 5. Instead, here at the output layer, which would have 10 output units, you would instead feed to the vector, which with a 1 in the 5th position, and then a bunch of zeros down here. Right? So the choice of number of input units and number of output units is maybe somewhat reasonably straightforward. And as for the number of hidden units and the number of hidden layers, a reasonable default is to use a single hidden layer. So this type of neural network shown on the left with just one hidden layer is probably the most common. Or if you use more than one hidden layer, again, a reasonable default will be to have the same number of hidden units in every single layer. So here we have 2 hidden layers, and each of these hidden layers has the same number, 5 of hidden units, and here we have 3 hidden layers, and each of them has the same number, that is 5 hidden units. But rather than doing this sort of network architecture on the left would be a perfectly reasonable default. And as for the number of hidden units, usually the more hidden units the better. It's just that if you have a lot of hidden units, it can become more computationally expensive, but very often having more hidden units is a good thing. And usually the number of hidden units in each layer will be maybe comparable to the dimension of x, comparable to the number of features, or it could be anywhere from same number of hidden units as input features to maybe twice of that to 3 or 4 times of that. So having a number of hidden units is comparable, or several times or somewhat bigger than the number of input features is often a useful thing to do. So hopefully this gives you one reasonable set of default choices for network architecture. And if you follow these guidelines, you probably get something that works well. But in a later set of videos where I'll talk specifically about advice for how to apply learning algorithms, I'll actually say a lot more about how to choose a neural network architecture. I actually have quite a lot more to say later about how to make good choices for the number of hidden units, number of hidden layers, and so on. Next, here's what we need to implement in order to train a neural network. There are actually 6 steps that I have 4 on this slide and 2 more steps on the next slide. First step is to set up the neural network and to randomly initialize the values of the weights. And we usually initialize the weights to small values near 0. Then we implement forward propagation so that we can input any input x to the neural network and compute h of x, which is this output vector of the y values. We then also implement code to compute this cost function j of theta. And next we implement backprop or the backpropagation algorithm to compute these partial derivatives terms, partial derivatives of j of theta with respect to the parameters. Concretely, to implement backprop, usually we will do that with a for loop over the training examples. Some of you may have heard of frankly, very advanced vectorization methods where you don't have a for loop over the M training examples, but the first time you're implementing backprop, there should almost certainly be a for loop in your code where you're iterating over the examples, x1, y1, then so you do forward prop and back prop on the first example, and then in the second iteration of the for loop, you do forward propagation and back propagation on the second example, and so on until you get through the final example. So there should be a for loop in your implementation of backprop, at least the first time you're implementing it. And then there are, frankly, somewhat complicated ways to do this without a for loop, but I definitely do not recommend trying to do that much more complicated version the first time you're trying to implement backprop. So concretely, we have a for loop over my M training examples, and inside the for loop, we're going to perform forward prop and back prop using just this one example. And what that means is that we're going to take xi and feed that to my input layer, perform forward prop, perform back prop, and that will give me all of these activations and all of these delta terms for all of the layers of all of my units in the neural network. Then, still inside this for loop, let me draw some curly braces just to show the scope of the for loop. This isn't Octave code, of course, but this is more like C++ Java code. But the for loop encompasses all this. We're going to compute those delta terms, which here's the formula that we gave earlier, plus delta L plus 1 times A L transpose, and then the sum of the code. And then finally, outside the for loop, having computed these delta terms, these accumulation terms, we would then have some other code, and then that will allow us to compute these partial derivative terms, right? And these partial derivative terms have to take into account the regularization term lambda as well. And so those formulas were given in an earlier video. So having done that, you now hopefully have code to compute these partial derivative terms. Next, in step 5, what I do is then use gradient checking to compare these partial derivative terms that were computed. So compare the versions computed using backpropagation versus the partial derivatives computed using the numerical estimates, that is using numerical estimates of the derivatives. So do gradient checking to make sure that both of these give you very similar values. Having done gradient checking, this now reassures us that our implementation of backpropagation is correct, and is then very important that we disable gradient checking because the gradient checking code is computationally very slow. And finally, we then use an optimization algorithm such as gradient descent or one of the advanced optimization methods such as LBFGS, conjugate gradient, as embodied in sort of FMIN, UNC, or other optimization methods. We use these together with backpropagation. So backpropagation is the thing that computes these partial derivatives for us. And so we know how to compute the cost function, we know how to compute the partial derivatives using backpropagation. So we can use one of these optimization methods to try to minimize j of theta as a function of the parameters theta. And by the way, for neural networks, this cost function j of theta is non-convex, or is not convex, and so it can theoretically be susceptible to local minima. And in fact, algorithms like gradient descent and the advanced optimization methods can, in theory, get stuck at local optima. But it turns out that in practice, this is not usually a huge problem. And even though we can't guarantee that these algorithms will find the global optima, usually algorithms like gradient descent will do a very good job minimizing this cost function j of theta and get to a very good local minimum, even if it doesn't get to the global optimum. Finally, gradient descents for a neural network might still seem a little bit magical. So let me just show one more figure to try to get better intuition about what gradient descent for a neural network is doing. This was actually similar to the figure that I was using earlier to explain gradient descent. So we have some cost function, and we have a number of parameters in our neural network. Right here, I've just written out 2 of the parameter values. In reality, of course, in a neural network, we can have lots of parameters. So these theta 1, theta 2, all of these are matrices, right? So we can have very high dimensional parameters, but because of the limitations of the sorts of plots we can draw, I'm pretending that we have only 2 parameters in this neural network, although obviously we have a lot more in practice. Now, this cost function j of theta measures how well the neural network fits the training data. So if you take a point like this one, down here, that's a point where j of theta is pretty low, and so this corresponds to a setting of the parameters. There's a setting of the parameters theta where, for most of the training examples, the output of my hypothesis, that's maybe pretty close to yi, and if this is true, then that's what causes my cost function to be pretty low. Whereas in contrast, if you were to take a value like that, a point like that corresponds to where for many training examples, the output of my neural network is far from the actual value yi that was observed in the training set. So points like this on the right correspond to where the hypothesis, where the neural network is outputting values on the training set that are far from yi, so it's not fitting the training set well, whereas points like this with low values of the cost function corresponds to where j of theta is low and therefore corresponds to where the neural network happens to be fitting my training set well, because this is what's needed to be true in order for j of theta to be small. So what gradient descent does is it will start from some random initial point like that out over there, and it will repeatedly go downhill. And so what backpropagation is doing is it's computing the direction of the gradient, and what gradient descent is doing is it's taking little steps downhill until hopefully it gets to, in this case, a pretty good local optimum. So when you implement backpropagation and use gradient descent or one of the advanced optimization methods, this picture sort of explains what the algorithm is doing. It's trying to find a value of the parameters where the output values of the neural network closely matches the values of the yi's observed in your training set. So hopefully this gives you a better sense of how the many different pieces of neural network learning fit together. In case, even after this video, in case you still feel like there are like a lot of different pieces and it's not entirely clear what some of them do or how all of these pieces come together, that's actually okay. Neural network learning and backpropagation is a complicated algorithm, and even though I've seen the math behind backpropagation for many years and I've used backpropagation, I think very successfully for many years, even today I still feel like I don't always have a great grasp of exactly what backpropagation is doing sometimes and of what the optimization process looks like of minimizing j of theta. And this is a much harder algorithm I feel like I have a much less good handle on exactly what this is doing compared to, say, linear regression or logistic regression, which were mathematically and conceptually much simpler and much cleaner algorithms. But so in case you feel the same way, that's actually perfectly okay. But if you do implement backpropagation, hopefully what you find is that this is one of the most powerful learning algorithms, and if you implement this algorithm, implement backpropagation, implement one of these optimization methods, you find that backpropagation will be able to fit very complex, powerful, nonlinear functions to your data, and this is one of the most effective learning algorithms we have today.